Associated with any particle is a matter wave called the wave function. According to the Born interpretation, the modulus squared of the wave function gives us the probability that a particle will be found in some region of space dx. A physically acceptable wave function must satisfy the following rules. It must be finite for all x. It must be single-valued, meaning that for any values of x and t, psi of x and t has a unique value. It must be continuous, and it must have continuous derivative for any finite potentials. Let's go through some functional forms and see if they're good or bad wave functions. Which of the following functions are candidates for the Schrödinger wave function of an actual physical system? We'll start with the wave function that looked like this. Now, there are three problems with this wave function. The first is that it's discontinuous. In other words, it jumps from here to here. Now, intuitively, a discontinuous wave function is a problem because that means that the probability of finding the particle at some location jumps to a much larger value, just moving infinitesimally further away. So, for instance, the probability of finding the particle at this position could be, say, 1%. But then infinitesimally close to that position, the probability would jump to, say, 80%. And so, intuitively, that doesn't make sense. More concretely, we know that the wave function must satisfy the Schrödinger equation. So, for instance, for stationary states, the time-independent Schrödinger equation is a second-order differential equation, which I've written here. And so, in particular, the second derivative of the wave function has to exist and be finite for any finite potential in order for the wave function to actually satisfy this equation. And at a jump discontinuity like this, the first derivative doesn't exist. And so the second derivative doesn't exist, and this wave function can't satisfy the Schrödinger equation. The other point to make here is that we have to be able to use the wave function to compute expectation values of operators. So for instance, the expectation value of the momentum operator, which is a differential operator, is proportional to the integral of psi star d psi dx over space. And if the first derivative of the wave function doesn't exist, which it doesn't at this jump discontinuity, then this expectation value is undefined, and I can't use my wave function to compute expectation values of differential operators. Okay, so there's other problems with this wave function. The second problem is that it doesn't go to 0 as x gets large. Now, this is a problem because if the wave function just stays at this constant value, then if I integrate the corresponding probability density over all space, I would get an infinite number. I would get infinity. And I need to be able to normalize my probability density so that I can use it to compute probabilities that particles will be in certain states. So if this wave function doesn't go to 0, this corresponds to an unnormalizable wave function, and I can't use it to compute probabilities. And finally, there's also a region of space where this wave function is double valued. And this doesn't make sense because what that means is that the probability of finding the particle at a certain position x is not unique. There are actually two different probabilities that the particle will be found at some position x, for instance. And this is clearly nonsensical. Okay, so this wave function was no good. Let's consider the next wave function, which looks like this. Now, this wave function is a problem because it goes to infinity, and it goes to infinity at multiple points. So the fact that the wave function goes to infinity means that when I integrate the probability density, the modulus squared of this wave function, I'm going to get infinity. And again, I'm not going to be able to normalize this wave function, which means I can't use it to compute probabilities. So that's a problem. The other problem is that when the wave function goes to infinity, at those places that means that the particle is definitely at the place where the wave function goes to infinity, and it has no chance of being anywhere else. So if this wave function goes to infinity at multiple places, as is the case here, then there are multiple places where the particle will definitely be found, which clearly physically doesn't make any sense. So this is also a bad wave function. Next, we'll consider the wave function that looks like this. So this wave function is continuous. There are no discontinuities. And it is normalizable. It goes to 0 as x gets large, so I could normalize it. The fact that it dips below the x-axis doesn't matter, because when I compute the modulus squared, I'm still going to get a positive number. So the probabilities I compute from this wave function will still be positive, even though the wave function is negative for a bit. The problem with this wave function is at this kink, it has no derivative. So as long as as we discussed over here, as long as the potential is finite, which we're going to use as a qualification of a physical potential, then I need the first derivative to exist. I need my function to be differentiable, which is not the case for a kink like this. So this is also a bad wave function for the reasons that the discontinuous wave function was bad. Finally, we'll consider the wave function that looked like this. So this wave function is continuous. It is differentiable. It is a smooth wave function. It is single valued. It is normalizable. I can use it to compute probabilities. And it doesn't go to infinity anywhere. So this is a perfectly fine wave function that could describe a physical particle. So wave functions are fundamental objects in quantum mechanics, and hopefully this exercise helped us gain some physical intuition as to what their form really means.